Hey, what's up, guys? So this is my own lecture about the good representation, and and I want to, and I will have the video about the algebra and the group representation in the future. But in this video, I want to try to at least give you guys a very simple example. It's a explicit construction of irreducible representation of SU2, and in the next video we talk about some basically algebra and its representation. Okay, so hope you guys subscribe to our channel. And previously, I already discussed that in a compact Lie group, basically you can construct a so-called hard measure. So once you have this hard measure, then you can basically prove all the similar theorem as the finite group, actual lemma, complex irreducibility characters. I mean, also one I just replace the summation of the inner product as the hard measure. Okay, so this video, let's talking about the explicit construction of representation of SU2. Okay, I'm not talking about quantum mechanics, so don't worry. Okay, so G is SU2. And no, let's consider to first representation V0. It's very obviously that you can define a so-called trivial representation. So basically, remember that group representation just G mapped to general linear group V. So trivial representation is the one dimension that every group element you just map to one. And the V1 is there's a standard representation. Right, so this trivial group is on C, one dimension, and this is on C squared. So basically, this V1 standard representation, because SU2 is 2x2 matrices, right? So SU2 is a standard 2x2 matrices, and such that it's unitary and the determinant is 1, right? So basically, let's say this is U, and the U is 1, and the det U is 1. Determinant U is 1, okay? Right, so standard representation basically given ABCD, right? So given ABCD, you just map it to ABCD. Okay, so yeah, so how about the Vn? Right, so what about n dimension? So let's using this to construct the standard n-dimensional representation, and the next time we can use the algebra to prove that these are all the unique one. Okay, so let's say Vn defined to be a homogeneous polynomial of degree n. So let me just write down homogeneous polynomial with degree n. Okay, with two variables, let's say z1 and z2. So this Vn is a vector space, right? Because two homogeneous polynomial of degree n summation is still the homogeneous polynomial degree n, and the times number is still a polynomial. So this is Vn is a vector space, so which is spanned by z1 and z1 n minus 1 z2, z1 n minus 2 z2 squared, go to z2 n. Right, and so this is dimension of Vn is just n plus 1. Okay, and so given any polynomial p, so given any polynomial p belongs to let's say z1 z2 with degree n, and then your G is ABCD, right? You take a group from SU2, and then you define the G egg on PZ. So this is definition, right? So G egg on PZ is defined to be P Z egg on G. So basically it's just P AZ1 plus BZ2 CZ. AZ1 plus CZ2 and the BZ1 plus DZ2. Okay. So you can write this P, right, in terms of your original basis, right? So basically you can write as original basis. So this is your representation. Okay, so this, so basically each G ABCD, right, you can write this as the these results as a representation. Maybe it's a little bit abstract, right? So let me just compute n equals to 2 for you guys. So it makes not easy to, maybe easy to understand. Yeah, so let's consider this, right? So suppose let's say P is z1 squared, And what's your GP, right? So your GP will become AZ1 plus CZ2 square. So you get A squared is D squared and 2ACZ1 Z2 right plus the C squared Z2 square. And also let's say P is Z2 square. So you get GP is BZ1 plus DZ2 square. So it's B squared Z1 square to BD Z1 Z2 plus D squared Z2 square. And if P is Z1 Z2 and your GP econ this P will be AZ1 CZ2 and BZ1 plus DZ2. So you can write is AB Z1 square AD plus CB Z1 CDZ2 square, right? So basically you can write your G. Now it's a 3x3 matrices by just write as a linear transformation of this basis, right? So I think it's A square to A1 to AC C square is sorry, yeah, should be here. So it's AB CD, Z1 Z2 AD plus BC. And this one is B squared to D squared and the 2BD. Okay, so this is the this is the representation. I mean, I guess you can check that. I mean, you can check by yourself. Yeah, hopefully this is correct. You can check by yourself. This G is basically satisfy the relationship such that the G partial the dagger at X on G will be 3x3 matrices. And also I think you can also check determine G should be 1. Okay. Yeah, so basically you can prove that this G forms a representation of SU2. Okay. And the proof is not difficult, right? Because if you act on G, G1P, G2P, right, act on Z will become P, Z, G1, and G2. And I mean, you can see that if you're become this is just right. This is just the definition, right? But I mean, if you want to, you can check this, right? So since it's 2x2 is identity, right? So if you act this G to be its dagger, then it will become identity, right? So you can prove that this is SU2. Okay, but let's just go to the key. Okay, so theorem. So we know that this is a representation of the SU2, right? So theorem says that these Vn are all. This is the non-trivial part or irreducible rep. And so basically every irreducible rep, so every irreducible rep will be one of it. So okay, so every irreducible representation of SU2 is isomorphic to one of Vn. So basically, it's a classification of the irreducible representation of SU2. Okay, let me just sketch a proof because the proof is a little bit lengthy. So let me just quickly say, okay, so I want to prove that Vn is irreducible, right? So by Schur's lemma, what we're going to prove is that suppose you have A from Vn to Vn, such that A is SU2 invariant, so A is SU2, or basically SU2 equivalent, then I need to show that A is A lambda I. Okay, so this is, I hope to show. Okay. So this means that if you have A, which is SU2 equivalent, right? So I want to prove this is lambda A. Okay, so basically, okay, so let's just use this. Okay, so let's consider a simple number at GA, right? So which is A0, 0, A inverse, which is SU2, right? Because it's unitary and I mean, it's Yeah, it's complex. I mean, if I mean A is my A is module is 1 and the determinant is 1. Okay. And then you can easily show that if you add on PK, right? Let's say PK. So I only care about basis, right? So PK Z1, Z2 defined to be Z1, K, Z2 minus K. Let's say K is from this. Okay, so GAPK will be A Z1K, A inverse Z2 minus K. So it will be A 2K minus N, Z1K, Z2 minus K. So it's PK, A 2K minus N. Right? So let's consider. So how about GAAPK? Right? So remember that's A is a map, right? So APK by definition, right? A is equivalent, so A will commute with GA, right? So A commute with GA PK, and GA PK is this, right? So it's A PK A 2K minus N, so it's PK A sorry, yeah, so it's A PK A 2K minus N, right? Because A will act on PK, okay? So from this, if you choose A, you can choose A, right? So A can be any complex number. If you choose A, be a module 1 with some of the complex number such that A2K minus N is different for each this part, then you can view that GA is a linear transformation and such that all the eigenvalues are different. So since all the eigenvalues are different, that means APK must be the eigenvector, okay? So APK must be CKPK. Let's say CK is a complex number. Okay, so first part. The second part is that let's consider RT to be cosine T minus sine T, sine T. Right, so your easy understanding is that this RT is basically belongs to the SU2. So basically it's a subset of SU2. Okay, and then you can check that by definition, right? If AR, you can use ART on PN, and A is commute with RT, right? By definition, so it's A. Let's say right. So let's say ARTPN will be A times Z1 cosine T by definition plus Z2 sine T to the power N, right? Okay, so write down everything. This is A and the summation of K. Let's say N choose K cosine KT sine N minus KT, and your A, right? Your A become your A can act on right. So this is PK, right? This is it become PK. Your A become PK. So let's write this APK. By this one, right, APK will become something called CKPK. Okay, so up to now, seems like we cannot. I mean, hard to see what's going on, right? But now, by definition, you can exchange these two, right? So get RTAPK. Okay, so what's APK? Just this, right? Sorry, RTAPN, right? So you get C and PN, right? So basically, this guy can be written as a RTCNPN, right? So it's RT CNPN, right? So RT act on this PN, right? Become the same thing, become this guy, and choose K. Oh, sorry. Oh, sorry. So it becomes N choose K cosine KT sine N minus KT. Right. This is the definition about N CNPN. Okay, so now you can see these two. you can see these two equations, right? You can see these two equations. One is CNP and one is CKPK, and the K is different, right? So in order for these two equation holds, every CK must be the same as CN. CK equals to CN for each K. So this means APK is just lambda, right? APK is just constant, right? Because APK become a CNPK for each K, right? So that means A looks like a CN times identity, which by this Schur's lemma, which Vn is irreducible. Okay, so okay. Okay, so let me just compute the final. Let's compute a character. Okay. Okay, and yeah, the character will help us to get an answer, to get proof that each irreducible representation must fall into one of the Vn. So let's talk about character. Right. So remember the character of, let's say, fix each n for a character for each group representation. G will become what? Will become its trace, right? So it's trace of G. Okay, so let's consider but I mean a little bit. So in general, you should compute every G, right? But this is hard to compute. But one idea that not very simple to see is that every element in SU2 is conjugate to, let's say, EIT 0 minus 0 negative EIT. Okay, this is not very easy to see, right? But let's first demand that this is correct. Okay, so that means all right, so let's call this ET, and then you can check that the ES is conjugate to ET if and only if S is plus or minus T. Okay, so it means if you have a function f from SU2 to complex number, then you can composite this function with this E. It become a real number, goes to complex number. Okay, but it's fine that let's working on this. Okay, so right, so let's say your G looks like this. And then for trivial representation, right? For trivial representation, let's use x0, right? It's everything is 1, right? Everything mapped to 1. How about 1? So 1 is the standard one, so it's EIT plus exponential negative EIT, so you get 2 cosine t. And then x2, you can easily check that. And so now z1 goes to z1 squared goes to exponential 2it z1 squared, and the z1 z2 become these two, right? So it's not still a constant, z1 times z2, and the z2 squared become exponential 2i minus 2it z2 squared. So for chi2 act on this G become exponential 2it plus 1 plus exponential negative 2it, which is 2 cosine 2t plus 1. And then you can easily prove that, yeah, so I mean, in general, exponential n, where you put EIT, will become a summation k from 0 to n, exponential I, n minus 2kt, which is exponential int, exponential I n minus 2t, exponential I n minus 4t, minus exponential negative int. And then you can prove by your simple trigonometric function formula to prove these famous results. This is a famous result that if you go to textbook, and you will see this guy, right? So this is just using this is what geometric series, right? The first term is exponential int, and the comma ratio is 1 minus exponential negative 2it, and then 1 minus exponential negative, let's say how many terms, right? So we should have 2n plus 1 term. Sorry, n plus 1 term. Sorry, yeah, n plus 1 term. Okay, then you can times this and do something you like. You can prove. Okay. Also, I mean, you can check if n is 0, which is 1. If n is 1, you get sine 2t divided by sine t, which is exactly 2 cosine t, right? So this is the proof of the character formula. Okay. So now let's prove the final result. So let's say we have chi be the character of w, which is irreducible. So let's say I got something representation called w, and then there chi is character, which chi is suppose that w is irreducible, but w is not the same as any vn. Okay, so chi be a character of w, which w is not isomorphic to vn for all n. Okay, then by orthogonality, right, this chi should be what? Chi should be orthogonal to every guy, right? So chi should be chi n equals to 0 for every n greater or equal to 0, right? Because chi is the irreducible representation. So this is a irreducible representation. So by Schur's lemma, so by orthogonality relation, you should commute with every. Should orthogonal for every character, right? And also you have chi 1. Okay. I mean, but you can easily show that this is contradiction, right? The reason is that all of your chi 0, chi 1, and chi 2 and chi 3, right? Your chi 3 will contain, let's say, cosine. Your chi 3 will contain cosine 3t, and keep going, right? So in terms of this, so this f is an even periodic function. So if your chi is orthogonal to all the cosine function, right? All the, let's say, cosine t, cosine 2t, and cosine 3t, and then finally you will get your chi n is 0. You're right. So finally, your chi x is 0, right? Because now your chi n contains all the cosine t, cosine 2, up to cosine nt, right? So n can be arbitrarily large. So basically, if you have an even function which is written as the Fourier series, but also going to all the cosine t, then your chi must be 0, right? But by definition, your orthogonality also requires chi inner product to be 1. So the orthogonality of all the cosine function already complete, right? So if you're complete, you're also going to every basis, then you should be 0. Right, so your chi should be 0, which is contradiction, right? So that means each irreducible representation of SU2 will fall into one of its construction. Okay, so this is the proof. See you guys next videos. Next video we talk about some basic Lie algebra and the representation of S, L to C, and I will give the very short introduction of Lie algebra. See you. Bye bye.